sometimes what you have is just a pulse, right? Something like that moves as one single thing. Okay? But sometimes what you have is something that's continuously shaking the medium, and then you get a pattern like Tian showed. I was going to do it on here, but because of the boundary at the end, it doesn't work as well. But if we take the slinky, and shake it like this. Yeah, you were doing a great job. You want to do it again? Okay, here, stretch that out. Okay. Well, actually, that's not bad. Okay, notice that that I've got one pulse following another pulse, right? And then I've just got one after another traveling down the end of the, traveling down the end of the spring, right? So the pulses are moving this way, okay? But they're occurring one after another, okay? In that case, instead of seeing like a single pulse that moves, we've got this continuous thing. And so, thank you.
I know, that's like amazing.
It's like we're hanging a noose or...
So, that pattern was roughly sinusoidal, okay? And meaning that if we say, here is my position x, and here is the amount of disturbance y, okay, then what we have is something that looks like this, and it repeats, okay? And you go, oh, this is the same graph that I drew the other night, but it isn't, okay? Because the other night, this horizontal axis meant time, okay? And in this case, the horizontal axis is a spatial axis, okay? We saw the wave, okay, distributed along the direction that it was traveling, okay? So, if we wanted to describe this wave, notice that it does have some of the same things that we saw with simple harmonic motion, okay? It has an amplitude, right? There's an amount that it was disturbed. If this were, in the case of that spring, when I was shaking it, it might be a distance of so many centimeters. Okay? In the case of a sound wave, it might be pressure. Maybe this is the atmospheric pressure, and this is so many psi above atmospheric pressure, and so many below atmospheric pressure. Okay? And that's what this would be measuring. In a longitudinal wave, it might be how far the coil was disturbed from its original position. Okay? And it could be disturbed one direction or the other direction. So this doesn't mean it has to be a transverse wave. This is just how much it was disturbed. Okay? And so we could say this has an amplitude. Also, there is a distance, there's the idea of a cycle, the distance from this peak to peak, okay? When we were talking about simple harmonic motion, that was time, right? But now, this is actual distance. This is how many meters there is between one peak or another, okay? So this is called lambda, which is the wavelength. And then we can do something similar to what we did the other day, where we said, all right, if the wavelength is the distance that it takes to do a complete cycle, and we could say that y, the amount of disturbance, is going to vary as we move along the direction of the wave, and after we've gone through a complete cycle, it'll come back to where it was before. So we could say for that wave, it's equal to A cosine, and then the amplitude, the disturbance is varying as we're moving along x, okay? So it's going to move along x, And after it's gone through one wavelength, okay, it needs to have gone through 2 pi, okay? So if this was one wavelength, I would want to be giving 2 pi to cosine. So I can do this. I can say x over lambda. So this starts off at 0. By the time x is equal to lambda, that would be 1. And then if I multiply this by 2 pi, right, then this would give me that graph, right? Okay. If I get halfway down the wavelength, so I'm at lambda over 2, I'm giving it pi, okay? And then when I get to 2 wavelengths, I get myself a lot of room, so I'm going to shrink it a little bit here. But a little bit later, this peak, the waves were moving that way, away from my hand. A little bit later, this peak is going to be further along, right? So this peak will be over here, okay? And then this trough, instead of being over here, will be over here. And this will go like this. That peak will be moved over. That peak will be moved over down here, okay? And it'll be the same wave, but shifted, right? It's shifted over this way. Maybe more like that, okay? And so what we can say is that, well, this should not only be a function of the position where we are along the wave, but it should also be a function of time, right? Because time matters as well. And the effect is this bump over here, okay, used to be where used to be at x equals 0. Now it's at a location that's somewhere in the positive, right? Okay. So what I need, so if this is somewhere in the positive, and well, back then it used to end up being something like this, but I need to make it look like this. In other words, I need to make this spot here look like what 0 used to look like. And this spot looks like, I need to make, I don't know, this peak here is shifted over. I need to make this spot look like what that used to look like. Everything needs to shift this way, okay? So if I want to make this spot look like what 0 is, I need to subtract off something, okay, as time goes on, so that this position x becomes, okay, where this spot was over here. Okay? So I need to shift the graph as time goes on, and I need to subtract something to get it to move like this. So this is going to end up being minus, okay, well, I'll write it the way your book did it, 2 pi t over over the period. Okay, so if this whatever the period of the wave is, how long it takes to repeat, okay? If we wait that much time, this ends up repeating, okay? And anyway, this would describe what that wave looks like as a function of x and then as a function of time, okay? So yesterday, when we were looking at simple harmonic motion, okay, one of the things we did was we said, well, we had A is equal to cosine omega t, right? Because omega was 2 pi over tau, right? But omega is 2 pi times the frequency, and frequency is 1 over the period, okay? So we can say it's omega t. We go, hey, 2 pi over lambda, 2 pi over the wavelength, it'd be nice to have a symbol for that. Your book doesn't use it, other books do. And unfortunately, it's called K, okay? But if you're doing statistics with other books, and you're doing cosine K x minus omega t, that's this same idea. This is called the wave number. That's the angular frequency. This is the wavelength. That's the period. Okay? You can be fine working with this, but be aware that that is out there. Cool. So this is kind of a weird thing. If you know a particular time, this would just become a number, and you would see that you can think about what the behavior would be if we looked at some particular x position, or if we looked at some time and we wanted to see what the shape is. The shape would always be sinusoidal. Looking at different, if we say, I'm going to look at a particular position, maybe 0, right over here, okay, what we would see is that this spot here would go back and forth just like simple harmonic motion, okay? And it would go with a period of t. Okay? But that's true for any point. If I pick some position over here and say, I'm imagining time going on, every time it goes through a capital T amount of time, it would go through one cycle of cosine. So you could imagine picking a spot over here and watching this move back and forth, right? Okay? Or you could say, I'm going to think about 55 seconds along, what's it look like, and it would be in this sinusoidal pattern just shifted. Okay? So that's kind of a... We haven't had functions of 2 variables very often, okay? So be aware that that's what that is, okay? Yeah?
So as things go along, the wavelength doesn't change at all. It stays constant, and then you're just kind of calculating over time where it's going to be at in this wave. Like
That's right.
What
That's right.
the
The whole
at a certain time.
As we saw with the pulse, the whole shape just moves along. Okay. Now what we're saying is, well, what if the whole shape is a long sinusoidal set of disturbances, like what we were doing with the slinky over there? In which case, they all just move along. Good. Yeah. Okay. It might be nice to think about, well, what does that mean? Well, okay, so we saw that with the slinky. I can sort of get some waves going like this, and so you can see that there's motion in time. Actually, this is a pattern that we'll talk about next time. But you see that there's a motion in time, okay, and a motion, in the spring. Actually, you aren't traveling; they're standing. And the waves we had over here were better with the open end because they didn't stand. With the water waves, you can keep shaking your finger up and down and end up with a pattern of waves that have a wavelength, right? That you can look and see the ripples and see the distance between the crests. And the pattern is that the distance stays the same and they just travel outwards, right? And so they all move together along. It's the same with the sound waves. You can't see sound waves like this and that, but it turns out that we can use this. This is a paper speaker, okay? And we can use that to observe, measure, okay, visualize the sound waves. So you're taking 115. So this is a paper cone, okay, and it is attached to a little coil, okay, a little wire We have, oh yeah.
Cheeto. Are they flaming hot?
Are
they flaming hot?
No.
Not a very good
God.
Oh, yeah, okay.
Right now.
See, I don't know, if you see, but there's a staple I just stuck to
That's true.
it, because it's magnetic there,
I
right? Okay, so there's a permanent magnet in here, there's a coil that's vibrating back and forth. If it vibrates back and forth around the coil, what does that do? Exactly, it induces an electric current, right? Okay, so it induces an electric current, okay? And this is hooked up to an oscilloscope. What it will do is it will sense that, it'll measure that. And the way an oscilloscope works is it has a little dot that moves vertically depending upon, it's actually the voltage that's applied, the voltage signal that's applied here. And as this goes back and forth and induces a current, it does so because it induces an EMF, which is a voltage, which pushes the current, and it's that. But that EMF is what is sensed by the oscilloscope. And so in the I'll turn on the oscilloscope, and there should be a, oh yeah, so there's this little dot. And notice that as I talk, the little dot goes up and down. So what's happening is that the cone is vibrating, and and so vertically this dot's going up and down. Can you see it? Yeah, yeah. If you can't see it from where you are, move over here. But it's also moving slowly across over time. Now what I can do is make it move faster, and when it does that, then we can see, if I do it fast enough, it can sort of capture what's going on with the sound wave. Oh, this is better. So you can see when I talk that I don't really make sinusoidal waves, but you can see the disturbance. Yeah? Okay. If we wanted to make a sinusoidal wave, how could I do it? Constant? What would have to be constant? Okay, so you're gonna go, ah! That was constant.
No, I don't have to repeat.
Yeah. So what does it sound like if you repeat? I need to make a tone, right? So, I don't know if I can do this. Oh, that's awful. Okay, I can whistle. Oh. That was better. Okay, so that was almost a sine wave, right? Okay. If you want, I'll leave this on later, and you can play with it, and you can see what your voice looks like, and also what sort of tones you can make. Okay. What was that? Oh yeah, okay. You'd want to do it longer. Okay. What other things make tones like that?
What, out of your mouth or?
Oh, I don't know. Well, we got this device now that can measure things. We should make a few tones and see what they look like.
Think of a chime.
What does it?
A chime.
A chime?
Do you have it?
See, you can make that aluminum rod or something.
Yeah, let's do that. Oh, yeah.
Pay attention.
What was that?
Oh, yeah. Oh, look at that. Wow.
It's like a seed.
It didn't work all that well, did it? I got a few other things. I have some tuning forks. Yeah. Oh, there we go. So it's not very good. Yeah, it didn't work as well. Okay. Other ideas? All right. Oh yeah.
So, one of my favorite Beyonce song. Actually, but before that was
Oh, yeah, yeah. Because the thing is like,
You have a glass one?
yeah, we try to learn how to
You like stick your finger in the water and like glass around the
yeah, without like signaling it, yeah.
I did, like, why do you
I
say
have
like
friends that are like
Oh.
super big Beyonce fans.
Oh, yeah.
All right.
They'd love me then.
Yeah.
Because at one point I was really
You
practicing
can find something
Halo.
you can do.
Oh
Singing
yeah.
Halo, trying to just like, yeah, right? I could do it. I could literally hit all the notes.
They would love you.
It was pretty
So-
fire. I spit hot fire. I'm not gonna lie.
For our perception, okay, with sound, what difference does well, changing the frequency? How do we perceive that? Yeah. High pitch, right? Okay. So let's see. If I can. That's a particular frequency. Let me see if I can do a lower one. Yeah, not so good. One of the things I have over here is a function generator. What it will do is it's also got a paper cone speaker like this, and what it does is it sends an electrical signal to the coil, which creates a magnetic field. Remember, there's a permanent magnet in here, which causes the speaker or the paper cone to move one way or another. Okay? If it does it so many times per second, that makes a sound wave that many times a second. So I can adjust this. Okay? And right now it says that's 453 times a second. If I make it go faster, what do we think is going to happen?
It's just gonna go louder.
It's going to be louder?
Higher pitch will go up.
Higher pitch? Higher pitch, louder? Are they the same thing? Now what's different? Loud, yeah, okay. Loudness is amplitude, okay? And so, let's see. I've got this one here. I'm gonna change the frequency. Okay, so now it's getting higher, lower. Yeah? Higher, lower. All right? I'm going to change the amplitude. Okay? This is lower, higher, lower, higher. So the pitch that you hear doesn't change, but it gets quieter or louder. Yeah? I can. Oh man, that makes it. Okay. Oh, right. There we go. Oh, yeah. Okay. Because this is a nice regular repeating thing, I can trigger on it, and it repeats this sound. So we can go, well, what happens to the, if I change the frequency and make it higher or lower? Okay? You can see that what I'm doing is sort of compressing these together or stretching them out. Well, that was okay. If I change the amplitude, okay, I'm doing this, right? I'm changing I'm changing the amplitude, I'm changing the loudness, but the pitch is still the same. Right? Okay. So those will affect the sound. I can also go really high. Yeah. Yeah. So lower frequency, higher frequency. You can see how this works. Leave that here. All right. Okay, so if we talked about what determines the speed of waves, okay, and we said that for something like this spring, or a spring, that the velocity is equal to the square root of the tension divided by the mass density. Okay. Sound waves have a speed. It's determined by the pressure of the air, okay, which is sort of like the force, okay, that is squishing the air together, the tension on this, okay, and it's also determined by the density of the air. Have you ever done things like gone to a helium tank and inhaled, and then, or a helium balloon, and then started talking?
Oh,
And if you do, your voice sounds
a lot more than
right? Squeaky and high pitched, even though you're talking in the normal way that you always do. Yeah? Okay? So that's because the pressure is still the same. Okay? It's still the same. You know, it's not high pressure helium or low pressure helium, but the density of the helium is lighter than the density of regular air. Okay? And so it ends up being a higher pitch. Okay? If you were to inhale some heavier thing, then your voice would be lower without trying, without, it just normally would go up or down depending upon that density. Okay? Your book doesn't talk about it, and it involves some more pressure and fluid dynamic stuff. Okay? But, so typically, and also, the speed of sound doesn't vary by much, okay, if you're in the air on the surface of the earth, okay, at standard atmospheric pressure, at regular room temperature, okay, the speed of sound is about 343 meters per second. Okay? So that's pretty fast, right? It's it's fast enough that I can talk, and you being, maybe 5-6 meters away from me, hear it pretty quickly. You don't think, oh my gosh, long delay, okay? But sometimes, you do notice things where light also travels. Light travels really, really fast, okay? Light travels at like 300,000 kilometers per second, okay? It's very fast, okay? So for things, or if you, sometimes you'll have the experience that you'll see something and then you'll hear it later. You have an airplane fly overhead, you see where the airplane is, and then you'll hear the sound as if it's following it, okay? And that's because the airplane may be a few kilometers away from you. It may take, at 343 meters per second, it takes about 3 seconds to go 1 kilometer, okay? So if it's a few kilometers away from you, you might hear the sound as if it were following it by 10 or 20 seconds. Okay. So that's created by the dynamics of how the air pressure works. This is created by the dynamics of the tension and the mass of the spring. Okay. But there's another relationship involving velocity that really just comes from with geometry. Okay? If we are thinking about if we've got a traveling wave, okay, and we've got a lot of peaks, and so here's one wavelength, and here's the next wavelength, and they're all traveling along like that, okay? Well, if the wavelength is how lambda is the number of meters per cycle. Okay? And the frequency is the number of cycles per second. Okay? So if the waves are traveling, okay, if during one period this peak travels over here, okay, and it's gone one period, okay, after the time it's gone through whatever the frequency number of periods, okay, then it will travel for 1 second, right? And so that will give you how many meters per second it is. So you can say that the velocity is equal to lambda f. Okay? If this meters per cycle, cycles per second, this is meters per second. Okay? And this is really just from the geometry, not the dynamics. Okay? And so it would apply to any traveling wave situation. Okay? So if you want to know if you say, you might say, all right, this is 388 cycles per second. Okay? So if it's 388 cycles per second, what's its wavelength? So F is 388 cycles per second, and V is equal to lambda F. Then I could say lambda is equal to F over V, which would be 388 over 343, which is going to be a little bit more than 1 meter, right? Okay? So that says that if we could visualize these sound waves, okay, I would have, maybe one peak coming out, and then a meter away would be the next peak, and about a little bit more than 2 meters away would be the second peak. Okay, that's how they're spaced. Okay, if I
Did you finish? Nice. What calc are you in? Calc
it's like doing it for compliant.
Oh, you didn't need that count?
Yeah. It's not that bad.
Yeah.
Yeah. Because like we use WebAssign. Like there's actually the problems. You didn't have to go class. Yeah.
Oh,
I
yeah.
turned it down
I've got
to
a couple teachers like that.
281, okay, and the waves are spacing out. I turn it
My
up higher,
calculator
they get
teacher is
closer
like that.
together.
My Calc 2.
Am I back
Talk
to
to
one?
Sparkle. What?
It's like upside down.
Calc 2? Dude, I couldn't. I like it.
No, but this shit is like easier.
Really?
Yeah. It's easier.
That's what everyone said. Like Calc 2 is like apparently
You
the hardest transition.
Yeah.
Like
Right.
Calc 1 was fine for me, but Calc 2 literally like I felt like I was busting my ass
Yeah.
and like getting a C.
Yeah.
And then it came down to the last test, and I knew I was gonna fail it. And something had happened. And I was just
So it's
like,
gonna be a little bit less than a meter.
Yeah, this is not that bad.
But,
You can just like,
thank you.
yeah. All you have
Yeah.
to do is just like understand it and just repeat it over and over again.
yeah.
Like with intervals, like just have
Dude, intervals. There's so many applications of use like an integral. And
Okay,
then
so the per second is
I
canceled,
know.
and made up with just meters.
integrating something was easy, but then like doing like every other part of math,
No,
I usually
wavelength is
do
just
like
meters.
figuring out like distances and like things
Okay,
like that.
it's
That just
the
sounds
distance
so
from one
easy.
peak to the next peak,
Yeah.
from one drop
This
to
shit
the
is
next.
it's just like,
Okay.
yeah, you have to find
Cool.
distances, but like in a 3D graph.
Mm,
Yeah,
Cool.
it's not that bad.
cool. Okay.
Okay,
I remember. Yeah, I remember we did it for years.
when a wave travels, okay, I expend some energy shaking this, right? Okay, and then the shake basically propagates down the end of the line, okay? And so the wave can be a means of transferring energy, right? I expend some energy there, and if you were down over here and had something that could, maybe capture, this shaking from the crank or something, you could use it to send energy from here to there, right? And actually, we use waves, or we take advantage of the fact that waves send energy. We get a lot of energy from the sun, either by growing plants or stuff like that, where the energy was produced over there, and it goes through a light wave and then comes over to us, right? Okay, so anyway, the radio signals, you can think of them as you're sensing, some energy that was produced at some transmitter, and you're sensing some of it further away, and that's what's delivering your data. So we can think about the waves as a means of transferring energy. If it's as the wave goes through, okay, the concentration of the energy might change, okay? So let's, with this, okay, if I pluck something over here, okay, and the disturbance goes down this spring, okay, all of it goes down the spring, okay? So if I shake this by a certain amount, I get the same intensity shake over there minus whatever little frictional loss happened along the way, right? Okay, but that might be pretty small, and in this case, it's not too bad. Okay, the biggest frictional loss is when it hits that pole on the other end and shakes. Okay, now if I come to this water tank, okay, and I disturb it, okay, and the ripples go. The ripple goes in a lot of different directions, right? So if I were to say I want to send some energy from where I plopped my finger in to a spot over here, well, a lot of the energy is going to all these other different places, right? So it's spreading out, okay? So what we would say is that the intensity is being reduced because the wave is spreading out. It's going off in 2 dimensions, okay? Sound waves have the same issue, okay? If I talk and it's louder right next to me, okay? And the people that are closer think that I'm a little louder, and people that are further away are less, because the energy per square meter, okay, is dropping off. Over here, the energy just goes one way. Over here, the energy gets distributed basically in a circle. There's this expanding circle, and if I delivered, say, 1 joule of energy here, okay, it would spread out, okay, all the way around here, and I get, so many joules per meter. If I were repeatedly doing this, okay, in joules per second, power, maybe I'm expending so many watts of pumping the water, okay, I'd get so many watts per meter at a further distance away, okay? Does that sound reasonable? Alright. So, we can say, all right, there is some object and it's creating some sort of waves. It's waves with some power P, okay? And if it's just on a spring, okay, we would expect over here to get P, right? Minus whatever little frictional losses we have, okay? If it's water waves, we'd say, all right, this is some source that's producing waves at power P. Those waves are spreading out in a circle. Okay? And if I look at some little chunk over here, okay, then the amount of power per watts per meter, okay, I get so many watts per meter, okay, and that would be P over, if we say this is some distance r, some away, watts per meter would be the total number of watts that were produced over here, divided by this whole circle, okay, so that would be divided by 2 pi r. Okay? So I'm going to do the next step. Suppose we've got some object that's producing waves of particular power, and this is producing 3-dimensional waves like sound waves. Okay? The sound waves are going to leave this. These are supposed to be concentric spheres. Okay? And okay. There you go. All right.
Cool.
So over here we had peaks, right? The peaks are spreading away. Over here, what we've got is the peaks form circles. So these would be ripples spreading out, okay? Over here, the peaks would actually be this shell, right? If I disturb the air and I make some sort of sound wave and it spreads in all directions, the peaks would move sort of radially away from me, not only this way, but that way, and that way, and that way. And it would form a sphere of where the peaks is, and it would get further and further away. Okay? If I go over here and I go, all right, I want to see how much power per square meter, so watts per meter squared, okay, I get over here, well that would be the power divided by the surface area, the original power got spread out over this whole surface area, and the surface area of the sphere is 4 pi r squared. Okay? So, let's see. This one, you just get the original power back. because it doesn't spread out. This one, you get whatever P over 2 pi r is. This one, P over the surface area. This has a name, which is called intensity. So we say the intensity of the sound wave is so many watts per square meter. Okay? I think this maybe ought to be called intensity, but it's not the same as that one. Okay, I'm not sure if this one has a name. Okay, but it is definitely the way that the power gets distributed. Okay, so the sound gets quieter, okay, it delivers less energy the further you get away. It's because of the three-dimensional nature that it's spreading out. And we could, you know, if we can measure the, you know, watts per square meter, we could quantify that intensity. It turns out that our ears are really very, very sensitive, and that we can hear, the quiet sounds that we hear are really a small number of watts per square meter, okay? Like a trillionth of a watt per square meter, okay? Which is it's not very much. And then we can also hear things, we can hear up to a watt per square meter, but that's kind of dangerous, okay? A thousandth of a watt per square meter is pretty loud, okay? But when you think about, the order over 12 orders of magnitude, from a trillionth to something, louder, a thousandth of a watt per square meter, that's a big range. So the first people to really quantify sound intensity, okay, were, well, when you think about sound intensity, does anybody ever work with it or know the name that we label for how loud a sound is?
Yeah.
Decibels, yeah, we use decibels, okay? So, decibel, that's one of the prefixes, right, for the metric system, right? Like you can have a decimeter, right, or a deciliter. It's not used all that often, but it means a tenth of, right? So this sort of implies that perhaps there's a unit called a bell, yeah, and that this is a tenth of it. And it's true, it is. Okay, the original unit for you go, why don't people measure things with just watts per meter? The range is really high. So in order to compress the range, okay, and to try and get it to match up with how we feel about the way sounds are, very quiet sounds and very loud sounds, it's hard for us to imagine that's a trillion times louder than something else. But it's not so hard to say, well, this on a scale, this is between 100 or 50 or something like that. So in order to get the numbers smaller, what the Bell scale is you say, well, I'm going to say that a bell is equal to the intensity, okay, but we're going to use the log of the intensity. And we'll use the log of the intensity, we'll divide by some reference intensity. And because this was done around the turn of the century, okay, and before easy natural logarithm tables were available, but there were lots of base 10 logarithm tables available. You know why there were lots of base 10 logarithm tables available?
What was it?
Right. Well, basically 10 because of your fingers, of course, okay? But the reason they computed them was they didn't have computers, and you could make slide rules out of them and do calculations using logarithm tables to make multiplication easier, like adding, okay? So they had a lot of log-based 10 tables. So it's the log base 10 of this, okay? So that's what a bell is, okay? After Alexander Graham Bell, it was developed by the Bell Telephone Company, right? And then, okay, so this reference is called the threshold of hearing. And it is 1 times 10 to the minus 12 watts per meter squared, okay? Which is teeny, right? Okay, it's a trillionth of a watt per meter squared. Your book has a table of decibel values and what they correspond to, and so, yeah, well, here, it says it's the threshold of hearing. It doesn't say it corresponds to something, but it says that, well, let's see. If you said, I want the intensity of the sound I'm measuring matches this threshold of hearing, that would be a bell of 0, right? Okay? If it's 10 times more than that, it would be a bell of 1. Okay? A bell of 1 is, they say, a person breathing at 3 meters. Okay? So imagine I'm standing away from you by like 3 meters, and you're listening to my breathing. Okay? Not labored, difficult breathing, but just normal breathing. My guess is that right now you can't hear it because there's too much other background noise. But imagine a really quiet room and that sort of thing. That's 1 bell or 10 decibels. Okay? And then they say a whisper is 20 decibels. Right? And it keeps going. By the time you get to a vacuum cleaner, it's 80 decibels. A jackhammer is 100 decibels. Okay? Anyway, they get louder and louder and louder.
Is that the beta, or is that just a mistake on the frequency?
No. Oh.
Bell is beta.
Well, hang on. So that's a bell. What's a decibel? Okay? The decibel is the beta, okay, on the equation sheet. And what we'll say is that beta is, well, for every bell, it's 10 decibels. So it's 10 times the log base 10 of the intensity over the reference intensity. Okay? So if you have something that is 70 decibels, okay, it's 7 bells, okay? So I divided by I naught would be 10 to the 7th, okay? Good. All right. So anyway, it turns out that by labeling these sounds like that, you can by labeling sounds with decibels, you can get an idea of how loud something is without using numbers like trillions and stuff like that. So I have this, which is it's the Radio Shack sound level meter. Okay, it measures things in decibels. Now, in order to use it, what I do is I tell it. Well, right now, I tell it a certain range that I think it might be, or at least I turn it to where I see the meter going. So right now, the meter is bouncing back. Sometimes the 0 is in the middle, and I've got -10 over here and +6. So if I keep it right at the middle, then it's at whatever this range value is, which it says is 80. Okay. Now that's probably me talking right at it. If you guys start talking, do I start talking?
No, I don't really want to start talking.
Now you're not as loud as me talking directly into your ear. So if I'll turn it down to 70, and now you guys talk.
What?
Okay?
No,
If I've got it down in the 60s, I'm reading the meter, but when
No,
I
because the bulb's
stop.
already lit, fam.
Oh,
Is that the best
so your
joke?
conversation is somewhere in the
Best
60s.
joke.
Yeah? Okay, so anyway,
I'm gonna piss down the basement.
if you're curious as to
So good.
what the sound is, decibel reading, you can, well, if it's something you can do in here, you're welcome to borrow this and check it out.
Yeah, you pass it around.
You should pass it around.
Sure. Check it out. Yeah, it's a nice toy.
Yeah.
We've been going for 56 minutes. We've been going for 56 minutes.
I didn't know what crown was actually a little piece of crown. It's on your mouth.
Take it with you. Well, don't forget my batteries.
You need a sash.
Huh?
You need a sash.
No, that's, I like to keep it close by. Otherwise, I have to wear a crown.
How am I supposed to know that? They'll just look inside. Oh, yeah, okay. Yeah, sorry. Royalty. Apparently, one of my good friends is royalty. He's related to the first king of Scotland. Yeah, it's crazy. There's probably still a little bit of incest in there, a little bit of those genes, but
Okay.
he's great, man.
So, the last thing I have for class today is they're appropriately themed, okay, in-class problem. Okay, so same rules as last time, okay, I'm happy, I would encourage you to work together, but I want everybody to hand in their own copy of their own version of work, okay? All right.
What? Okay.
Nobody's coming to class on Monday, right? It's 4th of July. Okay,
See,
let's imagine that you go
I'm still
and you
coming.
watch fireworks. Okay, so you're watching fireworks.
If I was from my head doing homework,
What's that?
I'm doing homework.
Hi, yeah. Okay, so fireworks, no, these are like, they're going to be further away and louder. I hope. I mean, okay. Okay. Now,
Fireworks.
suppose you see a flash, and then six seconds later, you hear a
You're
bang.
running? When you're running, or just like in general?
That is,
I watched a video of this guy behind Kim Kardashian, he just shows up. Just constant.
75 decibels.
She does it for a good while too. Like for a good while.
And
Let me see.
how far away was the explosion?
We all have to turn in.
343 times 6. 1800. 2056 meters. Times that by 3.1. So what is 2056 times 3.1. Alright, so what's 0.1 of 2056? 205.6. So 205.6. 2056 times 3. It's 6,160. Dude, add that together. 6,360. Oh, 73.6. That's how far it away is, bitches.
What is that in?
What?
What's the unit?
Feet. This is feet. So then you divide this by 5,280, which is how many feet are in a mile, and you get 1 whatever miles. But
They only wrote it in the metric system, right?
yeah, so 2056 is how many meters it's away. Hey, I just want to know for miles, okay?
How did you get miles in it?
So this is how much feet it's in. So if it's 353 feet per second of sound.
How did you end up with feet and miles?
Oh, this is meters. Well, I just converted meters to feet.
Why?
I don't know, to see how many miles I can. Just did it.
Yeah.
That's
That's
Hey, you
not
did all that in
really-
your head?
Yeah, what up?
You divided in your head too?
Oh, no, I didn't divide it. I didn't know this part. I don't know how to do this part. I don't know, this is like 1.1 or something. I don't know. But if it's 353, times that by 6, you get 2056, I think. I'm definitely not right.
It has like 20 horsepower.
Where's the explosion? We already know that one. What was the power of the explosion? I don't know. Oh, it was 2058. I was fucking. It's off by 2. I wrote 2056, and I can't do fucking math.
Damn.
3 times 6, 18. I just didn't have it.
You're close though.
Yeah, it's close. It's close.
There we go. All right. So
These for these tests are going to be.
you're watching fireworks, you see a flash. 6 seconds later, it takes actually quite a while, okay, for a fireworks display, you hear a bang that's 75 decibels. Okay? All right? Now, how far away was the explosion? How far are you from the fireworks? What is the power of the explosion? How many watts, okay, was dissipated at the time when the fireworks blew up? How much energy is released, okay, if the explosion took place in 0.3 milliseconds? So in other words, this is a burning chemical reaction. Very quickly it goes bang, okay? So it did that in 0.3 milliseconds. How much sound energy was released, okay? And then part D says if the explosive charge that created that firework was equivalent to 3 Nobel sticks of dynamite, okay? A Nobel stick, Alfred Nobel, the guy who took the Nobel Prize, made all his money by making dynamite. Okay?
Nice.
And so he, do you know the story about Nobel? Okay.
No.
He, so essentially, Nobel saw people mining, okay? And he saw them using nitroglycerin to mine, which is an explosive compound, but it's unstable and it's dangerous, right? Okay? And so it can blow up without warning. So he decided, I want to find a chemical explosive like nitroglycerin, but can be set off whenever you want it to and not accidentally. Okay? So he settled in on trinitrotoluene, which is CNT, which could be made into sticks of dynamite, which could be lit with a fuse and did not blow up if you shipped them by train or dropped them or any other thing. Okay? So he thought, wow, this is cool. I've made the world a lot safer place. Mining is going to be better now that I've invented dynamite. Okay? And then people started using it in wars, making bombs. He felt horribly guilty. So to get over his guilt, he started the Nobel Prize. Okay? Do you know why there's no Nobel Prize for math?
Why?
His wife had an affair with math. He might be able to do that. Okay.
Is that really?
Damn. I walked right into that.
So anyway, so a Nobel stick of dynamite has an explosive charge of 5 megajoules, or 5 million joules. Okay? So this was a 3-stick, okay, explosion. Okay? How efficient was it of converting that energy into sound? Good?
What is the power of this? Power.
Yeah.
The power. Of justice. In three-dimensional watts per meter squared, this power is equal to 4 pi r squared. We know the distance, so we just have to algebraically rework p over 4 pi r squared equaling I to find out how much power is actually released.
Yeah.
X is equal to A.
I'm still back here.
Right? Is that?
Hey, sorry, this is what I get for trying to do this off the top of my head. I should use, you know, the reason I make formula sheets is because I can't remember the formulas, okay? And, yeah, I should look them up.
What? I? So we don't.